welcome you in the lecture series of Basics of Communication Engineering. Now we will discuss about tutorial second. This is based on lecture third and fourth. The question first is a periodic signal has a bandwidth of 20 Hz. Here the highest frequency is 60 Hz in this band. What is the lowest frequency? And draw the spectrum if the signal contains all frequencies of the same amplitude. So here we know the bandwidth, it is equal to the difference between highest frequency component and lowest frequency component. Here the bandwidth is given 20 Hz and the highest frequency component is 60, and from this you can find out the lowest frequency component, it will be 40 Hz. So the lowest frequency component 40 Hz and highest frequency component 60 Hz. So we can sketch the spectrum, and the spectrum will have the lowest frequency component and highest frequency components, and in between, and all these frequency components having the same amplitude. So this is the sketch or draw of the spectrum having all frequencies of the same amplitude. Now another question. A non-periodic composite signal has a bandwidth of 200 kHz with the middle frequency of 140 kHz and peak amplitude of 20 volt. The two extreme frequencies, means lowest frequency and highest frequency, have the amplitude of 0. Draw the frequency domain of the signal. So here bandwidth is 200 kilohertz and middle is 140 kilohertz. That is lowest frequency must be, you can say, because the bandwidth is 200, so and middle is 140, so the lowest frequency it should be 40 and highest frequency it should be 240. So it is in kilohertz, 240 kilohertz, and the amplitude of the center frequency it is 20 volt, and the amplitude of the two extreme frequencies is 0. So using these given parameters we can draw the frequency spectrum of this signal, this composite signal. Now another question is, so that the complex exponential signal xt is equal to e to the power j omega naught t is the periodic and its fundamental period is 2 pi by omega naught. If xt is periodic, then xt will be equal to xt plus t, where t is the period. Means you can say e to the power j omega naught t is xt given. It will be equal to e to the power j omega naught t into e to the power j omega naught t. We must have omega naught t, e to the power j omega naught t, we should have it should be equal to 1. So if here, if omega naught is 0, this means xt is 1, and which is the periodic for any value of t. So for any value of t, this is the periodic signal. And if omega naught not equal to 0, this is not equal to 0, this means e to the power j omega naught t, it is equal to 0, it should be equal to 0. If here omega naught t is equal to 2 pi, it will be equal e to the power j omega naught t, it will be equal to 1. If omega naught t it is equal to 2 pi, since you know e to the power j 2 pi it is equal to 1, so the fundamental period from here it is 2 pi by omega naught. So this is the fundamental period of this complex exponential signal. You know, the Fourier transform is used to analyze the non-periodic signal. It represents the non-periodic signal in frequency domain. So if xt is the non-periodic signal, the Fourier transform of this signal xt, it will be integration minus infinity to infinity xt into e to the power minus j 2 pi ft dt. This is the formula for the Fourier transform of xt, or we can write it as minus infinity to infinity xt e to the power j omega t dt, and this can be represented as jf or j omega. And the inverse Fourier transform of x omega or xf, it will be f inverse xf, and it will be equal to the signal xt, and it is integration xf e to the power j, here it is plus j 2 pi ft dt, or I can write 1 by 2 pi integration minus infinity to infinity x omega e to the power j omega t d omega. This is inverse Fourier transform. So there is one example based on this Fourier transform. Obtain the Fourier transform of a rectangular pulse of duration t and amplitude a. This is the rectangular pulse, the duration is t and amplitude is a. The rectangular pulse can be expressed as, xt, it can be expressed rect t by t for the duration of t. It will be equal to 1. So for the duration of t, it's having amplitude a, where t between t by 2 to minus t by 2, and else it is 0. So this rectangular pulse can be represented in function form as this, and this is also known as gate function. So now Fourier transform of this xt, it will be integration minus infinity to infinity xt into e to the power minus j 2 pi ft dt using the Fourier transform formula. Or here I can write, because t is only between minus t by 2 to plus t by 2, so it will be integration minus t by 2 to plus t by 2, a xt will be here a, and e to the power minus j 2 pi ft dt, or I can write this as a by minus j 2 pi f e to the power minus j 2 pi ft, and limit is minus t by 2 to t by 2. So we can put the limit of value of t here. So we will have equal to a by f e to the power j pi ft minus e to the power minus j pi ft by 2j, or you can write it as a by pi f sine pi ft. Since this comes because sine theta, it is equal to e to the power j theta minus e to the power minus j theta by 2j, so it is sine pi ft, or I can write it as at by pi ft multiplied divided by t here, and sine pi ft. Also I can write it as at, and this part is sine pi ft by t by pi ft. So this is known as sinc function, sinc ft. It will be sine pi ft by pi ft. So this is sinc function at sinc ft. So you can see the Fourier transform of the rectangular signal xt, it will be at sinc function ft. So the sinc function is 0 at ft. So this function, it will be 0 at ft is equal to plus minus 1 plus minus 2 plus minus 3, all these integers value, this sinc function will have value 0. So from here I can write f is plus minus 1 by t plus minus 2 by t plus minus 3 by t. So f will be this. So at this value of f, the sinc function will be 0, or I can write the sinc ft, this function will having value 1 if ft is 0. So here you can see that the sinc ft, it is 0 where f is equal to 1 by plus minus 1 by t plus minus 2 by t plus minus 3 by t, and so on. And this sinc function it will be at sine ft. It will be equal to at when this function is 1. So this function will be 1 when ft is 0. That is, at t is equal to 0, the signal has value at only. So here we can sketch this sinc function at ft or f is equal to 0, this having maximum value 80, and f at f is equal to 1 by t, 2 by t, and 3 by t, this having value 0. So this is frequency spectrum or amplitude spectrum. And the amplitude spectrum, when I am going to take the mode of this amplitude, it will take only the positive value, or you can say it's the spectrum, amplitude spectrum of this sinc function. And in the phase, we can write phase spectrum, the phase shift of minus 180 degree to absorb the negative value of the mode xt and make it positive. And the energy spectrum of the rectangular pulse is in, if you want to find out the energy of this spectrum, it will be a square t square sinc square ft, and the power spectral density, it will be power spectral density, it will be equal to 1 by t a square t square sigma a square for f is equal to 0. Or you can say it is a square t sigma a square. Sigma a square is basically the variance in the amplitude. The bandwidth of a signal is the width of the frequency band in which 90% of its power located, or the bandwidth of a non-modulated signal is the smallest possible frequency for which its power spectrum density is 0. So the bandwidth of the signal is basically 1 by t, time period of the signal. Now another question, the loss in a cable is usually defined in dB per kilometer. If the signal at the beginning of the cable with minus 0.3 dB per kilometer has power of 2 milliwatt, what is the power of the signal at 5 kilometer? The initial, it is having 2 milliwatt power, and the loss is minus 0.3 dB per kilometer, and the length is 5 kilometer. So at this point, the loss in the cable, because 0.3 dB per kilometer loss, so in the 5 kilometer the loss will be 0.3 into 5, or you can say minus 1.5 dB, or 1.5 dB loss will be there. Here it is given that the power is 2 milliwatt at the initial point. So in dB I can write this loss as, and the loss is 20 log 10 P2 by P1. So it is 0.2 and it is 0.5. Power is P2 here at 0.2 and power P1 at 0.1. So the loss can be represented log 10 log 10 P2 by P1, and this loss is given as minus 1.5 dB. Or from here I can write P2 by P1, it will be 10 is to the power minus 1.5 by 10, or it will be 0.71, and I can write P2 will be 0.71 into P1. P1 is given 2 milliwatt, so the power at 0.2, it will be 1.4 milliwatt. So at 0.1, if the power is 2 milliwatt and the attenuation is minus 0.3 dB per kilometer, so at the distance 5 kilometer the power will be 1.4 milliwatt. So there is a reduction in the loss, minus 1.5 dB. Now the next question, what is the frequency of the signal in figure? So in this figure, in 4 millisecond, you can see in 4 millisecond there are 8 cycles completed. This is first, second, third, fourth, fifth, second, seventh. So in this 8 cycles are completed, the signal make 8 cycle in 4 seconds, so frequency will be 8 by 4 millisecond, or you can say 8 by 4 into 10 is to the power minus 3 hertz, or 2 kilohertz. So frequency is 2 kilohertz. So in the another question, a periodic composite signal with a bandwidth of 20 kilohertz is composed of two sine waves. The first one has a frequency of 10 kilohertz with a maximum amplitude of 30 volt, and the second has a maximum amplitude of 10 volt. Draw the frequency band. So here we have to draw the spectrum. The bandwidth is given and lowest frequency component is given. So the highest frequency component, it will be, you can see the highest frequency component, it will be the bandwidth plus lowest frequency component, and it is 20 plus it is 30 kilohertz. So we can sketch the spectrum here. This is 30 kilohertz, and this 30 kilohertz having the amplitude of 30 volt, and at 10 kilohertz it is having amplitude of 10 volt, and this is the bandwidth 20 kilohertz. Now another question, if the peak voltage of a signal is 30 times the peak voltage of the noise, what is the SNR in normal and in dB? So you know the SNR is signal power to the noise power, and we can say in voltage form signal voltage and noise voltage whole square of these, because power, the relation between power and voltage is whole square. Or here the peak voltage of a signal is 30 times the peak voltage of the noise, so this ratio is 30, so I can write it as 900. So this is SNR is 900, and in dB the SNR, it will be 10 log 10 900, and it will be 29.54 dB. The another question, we have the channel bandwidth of 5 kilohertz. If we want to send a data at 150 kbps, what is the minimum SNR in dB and in normal value? You know the channel capacity C is B log 2 1 plus SNR. So it is 150 given 150 kbps, and bandwidth is 5 kilohertz log 2 1 plus SNR. So here we can write 1 plus SNR, it will be 2 is to the power 30, or you can say SNR is 2 is to the power 30 minus 1, it will be 107374183 approximately. Or I can say SNR in dB, it will be 90.31 dB. So this is the end of the tutorial second. Thank you for listening this lecture.